Hey guys, and welcome back. So I think it's time we take a look at where we are with the means development. So things might look a little bit familiar, but also a little bit unfamiliar. This is the latest incarnation of the crane, and while this might look weird at the moment, when I start moving this thing around, it might actually start to make sense. So what we have here is, finally, I have like a proper arm that is modeled according to, or at least roughly according to how an actual real crane arm would move. You can't just move this thing around into any weird pose anymore, because you have to sort of take into account how this arm actually moves and what kind of poses it can strike, if you will. And this is kind of interesting. Like you can immediately see now that currently this thing sits on the right side of the vehicle, and suddenly we can't like reach as far as we used to do previously. So I also sort of lowered the movement speed of this thing a little bit so that it doesn't go completely crazy, all in an effort to try to actually make this sort of feel and look like an actual crane that would like probably weigh like 1 metric ton or something, just a crane, because this is a huge thing. Of course, if you remember, like we have a person is about that size. You can just see the scale of this crane arm. It's actually quite huge. And I hope now that we have this crane arm here, you can start to appreciate this movement of the cable and everything on a whole different level than when it's just sort of something floating in the air and not really looking like anything. But yes, I think for those of you who have seen my previous videos, this might look sort of underwhelming. Like, okay, what is this? Why has it taken like a week to get this arm going? And it hasn't. I've been actually exposing lots and lots of things from the engine side over to SIG so that we can actually work in ZIG now. And for those of you who aren't aware, the engine is in C++. The game is written in ZIG. And one of the new big nice things is that this crane is also now in ZIG. We have this new cargo crane component here, and I will split the functionality of this. I'm sort of anticipating that I might create several of these cranes and configurations. So actually this thing just has an arm, which is really this thing which isn't really rendered yet, only using these debug spheres and lines. And then you have this thing called the, what did I call it? Crane cable magnet assembly. So the crane cable magnet assembly is this thing which wraps this whole idea of a cable that hangs from something and that you can actually lift things with. So if we just put a vehicle slightly closer here, it handles this whole thing of extending and retracting the cable, and you can actually lift things with this. And all of this is now finally in ZIG, so that's nice. You can do all of this now like we used to do. So actually there's been quite a lot of things that I've had to do to actually make this possible to do in ZIG. No C++ involved in this crane logic anymore, except for the things that are on the engine side, obviously. And yeah, this doesn't look super different than the C++ version of the crane, except the fact that we have this arm now, and it sort of moves how an arm would actually move. But yes, this code is now much more sort of production quality, if you will. The one thing that I don't have here, which I had in the C++ version, I mean, obviously we're lacking a lot of we're lacking essentially all graphics. That's something that's going to come next. But before we do that, the one thing that I had in the C++ version and that we don't have in this version is this idea of packing these points that we want to send to the client, because this whole thing essentially runs on the server. Right? If you have a look at this cargo crane component, we have a function here called, what is it called? It's called onObjectCreated. It creates the arm, and then it creates the cable magnet assembly. If you go into one of these guys, you can see that it has these on-server checks everywhere where we actually deal with the physics, create physics parts, then goes in and creates like the fixture, which is this thing here, which as you extend or retract the cable, this thing sort of jumps up and down and adds more of these segments as the fixture. Then we have the cable parts, and then we have the magnet, which is this thing here. So all of this is only created on the server, right? And we still want to render it on the client. This is kind of the same thing that I explained in the last video. So if you want to have a look at that and want to know more, have a look at the previous video. Anyway, we don't actually send that information to the client in this Zig version at all. And so I figured maybe we could try to actually do that in this version. And then when we have that thing working, we can finally actually start to look at adding meshes here. And when we have the meshes, then this thing will actually finally be sort of done, at least for now, when we can move on to something completely different, like, I don't know, level design or missions or something. Because yes, this crane has taken up like a month of development now, and I'm getting a little tired of it. But anyway, let's have a quick look at the C++ version. So this is not really production quality code that we have here, but the idea, I think, is pretty good. So in the tick function, again, only on the server, we have this thing called packVisPoints, which we'll probably call something different, but it like the name suggests, it packs the visualization points for the cable. And when we have that, it actually packs them into this buffer here that we don't actually see. And it packs the visualization point bounds. And then we write that to a pipe. And the pipes are actually something that I've only recently added. It's not something that has existed in the game engine for a very long time. But a pipe is essentially a way for a component to communicate with itself across the network, like the server representation in this case can send data, and just any data. This is just a byte buffer, byte array. And you can just write that buffer to the pipe, and it will appear on the other side of the network, in this case in the onPipeDataReceived function here. And we assert that we are actually on the client in this case. And we can get those points out of there. And if we look at this, what is this? Well, it's a vector of uint32s. So really, that is what we're working with. We're dealing with a vector of 32-bit unsigned integers and an axis-aligned bounding box AABB for the bounds. Using those, we can then recreate the cable visualization on the client. The packVisPoints and then unpackVisPoints. Let's have a look at packVisPoints first. This is the thing that we're going to write today in Zig. So first of all, figure out the bounds. We add the point, or we clear the bounds, and then we add the points there. Essentially, we're iterating over all the segments. And then when we have the bounds, we can actually use the bounds here. And what we do here is we scale the or we remap the actual point for each cable segment into this range of 0 to either 2047 or 1023. 11 bits for 2047 and 10 bits for 1023. And then we have this interesting thing here with a union called a packed point. And we have 3 coordinates, so x, y, and z, 11 bits, 10 bits, and 11 bits. And if you want to know more about why I chose these exact bit patterns, then have a look at the previous video, but basically these add up to 32, which means that we can also just use one uint32 when we send it across the network. And so that's what we do. We have this U32 here, which we push to the vis points. And that's how we pack the whole data into a third of the original 3 float vector trees that these come in as. So these guys. And then when we unpack them, we do essentially the reverse thing. So we take those uint32s, we create a packed point out of them, we set this U32, but then we read them out as floats. And then we need to remap them back into the normal world bounds. And that's it, basically. We do a subtraction of parent position as the first thing we do here. So we need to add that back in when we remove them out. And unpack vis points, then of course this is used on the client. So in update, and once we have that, actually what I do here, and I'm not sure if I can actually do this on Zig yet, I construct a Bezier smooth curve path from these positions. I might not actually have exposed this to Zig, so we might not be able to do that. But we can at least draw the unpacked points and make sure that they look correct. I may have to port some more code over from C++ to Zig, which I'm not gonna do on video because it's not super interesting. Except that is exactly what we're doing here. But at least this is gameplay code and not like tech code. And I don't want to bore you with tech stuff. So that is what we're going to do today, and I hope I will be able to do this in Zig. This is completely unscripted. This is completely unprepared for. I just figured, hey, let's do some work and let's make a video out of it, and at the same time you guys get some insight into what's going on. And yeah, we'll get to eventually getting this crane finished. So I'm going to move this thing off to the side to my second monitor. We can move the header there as well. And so where is this thing going to go? Well, it is going to go into the crane cable magnet assembly, because again, this is the thing that manages the actual cable and magnet. And we have this update method here, which we will I am sure we will use for this exact thing. We will unpack the data there. But before we can unpack the data, we need to pack the data. And I think we will do that here in the tick function. I'm going to have a quick look at the C++ code to verify. And yes, indeed, we only want to pack them on the server. So let's have a look here at how do we actually update this guy. So we have tick here. This runs on both client and server. And so we do some checks here. Not sure we actually need. Well, eventually we'll probably need to do things on the server and the client here in the ARM code. So let's leave this as it is. But we have like this on server check here for doing server only things. So tick again, is called on both client and server here, and I think we'll probably need to do something on the client here as well. So we'll add this if here to isolate this server only thing. And what is the server only thing? Well, it is of course the packing of the data. So create physics parts, destroy physics parts, extend cable, retract cable, toggle magnet. Here is where we can actually do that. So let's call this pack, and let's not call it viz points because that's kind of ambiguous. Let's call it cable points or something like that. Right, and this will be self because it is a method, and I think that the other version took the position, but I wonder if we actually want to do that here. Let's do it. Let's do it here as well. I think the reason why I want to pass it separately will become clear later on. Parent position, and that would be a vec3. Right. And so this will be a void. I wonder if this will actually need to throw some errors. It might be. If it needs to throw errors, we need to add like an exclamation point before the void. Let's keep it like this for now. If we save, it will add the unused or the ignores there. So we have an AABB class. Well, it's not a class, it's a struct in Zig. But yes, we do have this guy, and I think I want to actually I want to add one of these guys here. So let's do cable point bounce, and this is a basis math AABB, and maybe we can even init empty, right? And that should give us, yeah, gives us an empty AABB. And now I wonder, like we need to allocate like a buffer for this whole thing, and this is where this stuff kind of gets a little not tricky, but I haven't really done this before. Let's see if we have an allocator. How do we do this? We have an allocator. We want to allocate. We want to allocate some bytes. And how many bytes? This looks really easy. So if we do U8 and we want to allocate, let's say, 1 megabyte of this. I mean, it's more than we will need. Anyway, if we do that, then what we get is essentially what do we get? We get like a something like this. We get a slice of U8s, right? Right. And then we can do defer context allocator. Is it free? I think it's probably free bytes, right? Does that work? I think that should work. Oh, right. Okay. Like, yeah. Yeah. Right. So this would need to be something like try. Oh, woo. Something like that, and then we need to actually do that, and then now we probably need to try somewhere higher up in the thing, right? Let's see, cargo crane component, blah blah blah. Yeah, this needs to be a try as well. Now that should, I guess, probably work. I guess, maybe, hopefully. Doing new things for the first time. It's always scary. So basically what I'm thinking is that we'll yes, that succeeded, and it probably actually also works. If we can get into the game, then it means it worked, yes. So what we did here in the previous version, or in the C++ version rather, let's bring this over quickly, is that we have just a buffer here on the stack, temp buffer 512 bytes, which is probably enough, and we might want to use the same size, but maybe we'll go crazy and allocate 1K. But I'd rather not do it on the stack if I can avoid it, because stack space is sort of precious after all. So let's do it like this. We do how do we do this? Cable point buffer, and this would be a U8, right? That's a U8, and we probably need to actually initialize that to something. So how do we do that? I mean, that won't work. Missing struct field cable point buffer, because we need to do something with this. So let's have a look here. The reference, the language reference, slices. Yes, slices. What do we initialize slices to? I wonder if like slices would the correct thing to do here be to actually I think the correct thing to do here might actually just be to have this as an optional thing, right? And then just initialize it to null. Like that would work, right? Because there's only really ever one place where we need this, I think. Actually, that might not be completely true. Might want to use it in a few places. But anyway, yeah, we can keep this as an optional for now. And the thing is, though, that like if we have this, I mean, a slice is just like a pointer and a length, right? So what about, can we do something like well, language server is just going crazy. Like if we just Google this for a bit, like zig empty slice, right? How do I create an empty slice? Right, you can do this. So address of like an, what is that? Like a tuple or an? Yeah. That would mean that I can do this address of that, right? That should be fine. And then later on I can actually go in and change that to something. Maybe that's like better, essentially. I don't know. Maybe it's better. Yeah, that succeeds at least. Let's leave it like that, and then we can do here. We can do. Oh no, I don't actually need to. Yeah, yeah. I'm being stupid here. I'm sorry. I'm sorry. I'm being stupid here. What we actually want to do here is this. Let's put here a so a cable point buffer size, and we'll go with a with a 1K buffer for now. I know this is perhaps not how Zig constants are named, but it is how I name them. So it is what it is. Yeah, because this is the init function that we are in right now, like this guy here, which is essentially like the constructor for this guy. If we don't assign something here, we need to assign to it here in the init function. So now if we try to build this, right? I'm sort of explaining this out because I'm verifying it myself. So now it's going like, missing struct field, can't do that. But if we now do try context allocator alloc u8, and the size would then be cable point buffer size, right? Now it would work, right? Yes, now it works. And now in the destroy, which typically would be called dinit in basis, but or in Zig, but I'm calling it destroy here because it maps to the destroy method in the component. This is where we would want to free it. So let's do self.context.allocator.free, and we would do self.cablePointBuffer, like so. And that should work as well. And it does. Okay, cool. Yeah, so I could have initialized that there, but I don't really need to do it. We have some other things here that we don't initialize. Like we don't initialize that because we initialize it here. And we have cable segments as well that we don't initialize either because we also initialize it here. So essentially things that require the allocator to be sort of passed in here as part of the context. I initialize here. Okay, good. All right, and so now we have the buffer there, and when we have the buffer, we should be able to actually do the rest of this packing quite easily. Let's go to our pack method. Where's the pack method? It's right here. Okay. So parent position, we need to pass that in. We're not calling this anywhere. Let's do that. Let's go to tick, I think, here, and want the position. Okay, so we can do const pos equals self context transform get position, and that is the world position of the parent object, essentially, of this component. Then we can do self.pack cable points, and we pass in the position like that. Boom. And in here, we can now do right. So I'm going to copy this comment here because it's quite good actually. So we subtract the parent position, i.e. the vehicle position, from the world space position to get the points in the unrotated local space of the vehicle. That is kind of important. We're not putting them in the local space because that would, well, it's a point, so it doesn't really have a rotation. But the idea here is that we have the unrotated world space, an axis-aligned bounding box where the axes are aligned with the world space axis. So we don't have to use any like transform matrices or anything like that. We can just use the position, and we can subtract from the position. So we do self cable point bounds dot clear, because obviously this thing will be run over and over again. So there will be like old bounds from the previous frame there. And then we do for self, and yeah, ZLS is being a little difficult to work with sometimes. Anyway, we have the cable segments, and we have items, and that would give us a slice, right? So we can do for this slice, we get the segment out. We can just use S for that, for example. And S has a rigid body, And the rigid body has a world transform. Yes. The world transform arguably has a position, so we can just do const pause for that, and you can actually immediately we can subtract the parent position out of that. So now we get the pos that we want. The position in the unrotated local space of the vehicle, right? So cable point bounds, yes, and add point and pos, right? So when we have done this, we actually we have all of those we have the bounds that we looked at in the previous video for the cable. I'm sorry, I'm just my brain is not working today clearly. Cool. Okay. So what we could do now that we have this thing, we haven't packed any points yet, but we have the bounds. What we could actually do now is do the receiving side just straight away, and we can simply unpack this bounds object and render it on the client. Make sure that the pipe works, for example. I've never used any pipes from Zig, and all of that. So that should be a pretty good first step to do. Right, so we have this bounds object on both client and server, obviously, because they're members of this guy. We also have this buffer. That should also be good. So now we need to use something called a binary buffer to pack all of this stuff. So we pack the cable points. Let's pretend for a moment that we also have put the points in there. And what we want to do now is we'll want to use the buffer that we used. So we'll do a stream. The stream is a basis binary stream, binary write stream, and we need to init it, and we'll init it with the what did we call it? It was cable point buffer. Actually, let's not call it cable point buffer. Let's call it cable visuals buffer or something like that, because it will contain other things beside the points. It will contain the bounds, obviously, but it will also contain other things in the future, like the end of the cable has the magnet, and we'll want to send the magnet's transform as well. So let's call this cable visualization buffer. Visualization buffer. What is it with me today? I can't write. I can't do anything. I can't talk. Okay, cable visualization buffer, cable visualization buffer, and cable visualization buffer, and we have the same thing here with cable visualization buffer. Right, little endian can be true. That's completely fine. Now that we have the stream, we can just do stream dot put put. Do we really need to give it the type? That seems weird, but maybe that was how it worked. Yeah, okay, so you can put some ints and bools and floats, strings into it, but if you want to do something more fancy, you need to give it the type, and we'll call serialize on it. I wonder if our bounds object is actually serialized, but let's assume it is. So that would mean that we would give it basis, math, ABB, and then we will give it self dot cable point bounce. And now I wonder if this actually works. Right, so we'll go like, I don't have a serialized method. I don't have a serialized method. Okay, well, I'll give you one then. Right, so good. Okay, so we need essentially these two guys. We can put them, where did Vec3 have them? Where in the file did it have them? It was right towards the bottom. That sounds good. That sounds good. So we'll do self and self, and we can do this guy probably has a min and a max and a hash points. Okay. Okay. So self min we can do vec3 deserialize. Oh, we need to. Interesting. Okay, so we don't do that. We do self.min.deserialize, right? And then we do pass it the stream. That's how we do it. And then we do self.max.deserialize and stream again. And then we do self.hashpoints is that would be stream.getBool. Let me just quickly have a look here and on the C++ side to make sure that that is actually how we serialize or deserialize one of these guys. And of course I can't find it. That would be too easy. Min and max. We don't actually serialize hash points. That's kind of bad actually. Why don't we have that? Maybe it doesn't have one of those guys on the C++ side. It does. Okay. Oh boy. Well, yeah, I'm gonna have to actually look at that at some point. I mean, this is how it's supposed to be, but we're not doing it there, and I want this to be binary compatible with the C++ side, so I can't just willy-nilly go and add it there either. Yeah, that's stupid. That's stupid. So basically stream.putBool, right? And then self.hashpoints. Yeah, I need to write a bug about this. Just a note to myself. I can get rid of that for now. Yeah, because it's like this is what it looks like on the C++ side. I'm just going to copy this guy over. Like it looks like that. We just get the minimum and the maximum and we put them in, and that's not good. That's not good because we leave out the hash points. And in fact, maybe I've been smart about this. Have I been smart about this? Yeah, I've been smart about this. Because basically when we're deserializing, it looks like this. And then this val.set actually sets the value of hash points. So this is not actually I've just saved like a byte there in my serialization. Right, so let's get rid of that. We don't really need that. We can just determine here that okay. We let's see, we add a point and it just sets it to true. Yeah. Okay, well, we could do something like this. We could do actually it's in the deserialization is where we need this. We could do something like var min vec3 is, you know, undefined, and we can do var max, same thing, and then we can just do like that, and then we can do self dot add point min and self dot add point max, and now when we add these points, it actually sets it to true. So yeah, I don't know. That seems so dirty somehow. Anyway, now we can actually serialize this guy, and now if we build this, it should build. And we can put this guy here, and it does. So that's good. And now if we have this, we should actually be able to simply write to the pipe. But before that, of course we need to actually create the pipe. So let's do cable visualization pipe, and this is a basis network pipe ID. And this is really just a U64, so an unsigned 64-bit integer. And where do we actually create that? On the C++ side, we create it in the create function. And we need to do it on both sides, so both on the client and server, otherwise the pipe is not fully valid. So cable visualization pipe, we do self, we do context, we do create, we do register pipe is what we call it. And we call this, this just needs to be unique within the component, but we can create it, call it cable visualization pipe. And this would be basis network pipe direction server to client, so we can just call it dot server to client. Reliable? Nah, it doesn't need to be reliable. That's fine. So that's how you register a pipe. That's essentially the only thing we need to do. We need to initialize it somehow though, and we can just set it to 0. And now we can write to the pipe. So we go here. We have this this buffer that we've created, and this obviously is larger than just this one thing. So we need to somehow come up with a slice that is just the data that we've actually written, and I think we can do it like this. We can do written data is, actually we can just call it data. Data is self cable visualization buffer, and it goes from 0 to stream cursor position. And then we can do self context write to pipe. We give it the pipe. Yeah, come on. Cable visualization pipe, and data is data. Right. Yeah, that should be it. Now we're serializing those bounds on the server. Because we're on the server, we are writing them to stream here. We're getting the data, which is this buffer, goes from the first byte to the cursor position, which is like how far we have actually written. Then we're taking that data and we're writing it to the pipe. Let's just make sure that builds. And it does. Excellent. Okay. So that's cool. Now we're sending the data. And here, of course, now we are on the client side. So what we can do here, we can assert some things. First of all, basically assert that the pipe is actually self.pipe ID. So it's cable visualization pipe. That's fine. We also need to assert that, or we don't need to, but we can assert that that we're on the client here. Like when we are registering this pipe, we are setting it the direction server to client. There's no other direction currently. I added a comment here that one day we'll have client to server and bidirectional, but I haven't implemented those yet. So currently this on pipe data received will only ever get called on the client, and even in this case it would not be called on the server because we don't have any data that we're sending from the client to the server. Right, and now we can create a stream again, and this would be basis binary stream, binary read stream. And of course we need to initialize it like this, and we give it the data, and up. Little endian is again true. And out of the stream we can get a basis math AABB, and what do we need to do? We need to actually it returns one, right? Okay, so this would be self visualize. Okay, well, the cable point bounce. That's what we want, right? Yes, and that's it really. This is now we have the bounce on the client. So pretty easy. And now we can do, if we are here, if self context on client, yeah, let's leave that as it is. Let's add this this second thing here where we have the cable point bounds has points, right? If it has points, then we will debug draw it. And just this, I think this should, doesn't this take like a, right, okay, white is the color. That's probably fine. We can leave it like that. I'll try to build in release mode. Let's see if this actually works. So we're obviously we're drawing all kinds of things now in sort of for debug purposes or development purposes, but most of the things we're actually drawing on the server directly. Oh, we're getting some interesting. Yeah, that doesn't seem right. I think I know what's going on here. Is it actually? Yeah, like it is updating. So probably what's going on here is the fact that we need to sort of unpack them. We need to take away that like this thing, right? Actually, it's like that. Now we can just to make sure that is actually the problem here. Like we don't really need to actually debug draw that, and I don't want to like put in any additional transforming code there to make sure that it gets like rendered correctly, because we don't need to render it really. But just to make sure that that's actually what's going on. Oh, it is not though. It is really not though. Are we not writing the min-max? Min-max. All of this looks pretty good. What we might want to do is actually clear it before we do anything else. That sounds like a good idea. Oh. Yeah, that's probably what we did, because we have this. We don't use the set function. We don't actually even have a set function here. We just used add point, and add point just adds a new point to the bounds. Like it potentially makes them larger. Yeah, but that didn't seem to be the case. Like that seems like it is like roughly the world origin that we're seeing. So I wonder if we have, yeah, that's probably the world origin there. Like this corner is probably sitting at the world origin, I would imagine. So that's weird. That's not what we want. There might be just like a bug here in this zig version of these bounds, but this is important because obviously it won't actually work like this. Like this sets it to 0. That sounds a little strange. Sounds a little strange. Like these shouldn't be 0. Right? They should be. Yeah, they shouldn't be 0. Because now what we're doing is we have a point at 0. Yeah, this is the bug actually. We have a point at 0 here, and we want to actually the minimum of the bounds, it sits somewhere around here, and it's probably higher than the minimum. So the minimum needs to be initialized to something really large, and the maximum needs to be initialized to something really small, and that is what I'm doing on the C++ side. For some reason, I've done it stupidly here. So yeah, like max needs to be essentially initialized to, what do we have? We have like basis math, largest number, something like this, and this needs to be like negative largest number for all the components. Right? Oh, something like that. So the maximum is the essentially now the smallest number, because we're doing negative components, and the minimum needs to be the largest number. So that when we add a point, if it is smaller than this, then it gets added. Yeah, this should be much better. So all of a sudden we're fixing bugs in the math code here on the SIG side. Yeah. And now we can see what is going on. What is going on? Okay, so now it looks better. We can see the bounds getting calculated here. We don't really have any bounds when we have that short of a cable, but now if we make it longer, we can see the bounds starting to get updated properly. So this looks better. That's much better. That is much better. Good. Okay. And yeah, this doesn't look all that interesting, perhaps, but these white bounds now, they're getting sent over the network from the server to the client and getting rendered on the client. So there's quite a lot of complexity here. Okay, so now that we know that we can render them properly, I'm going to put back that subtraction there, and we can probably actually just remove this debug drawing, because we can remove all of that. We'll be drawing the cable with some debug drawing just in a second, but we won't be actually drawing the bounds necessarily. Okay. Now then. All right. Apologies for that. My phone rang. Yeah, I kind of lost my train of thought. But basically, what we want to do now is actually pack those points finally, and that'll be interesting because I haven't really done any like bit packing in Zig, but I think I found some functionality for doing that. But before we go into that, let's just let's set up some things here. So we'll need to have a buffer of those packed points, just like we have on the C++ side. So we'll have cable packed visualization points, and this would be like an std vector or std vector on C++ side. On Zig, we call it an array list instead. I think that is the closest equivalent. So we do that, and then we do std array list u32, and we init it with the contexts allocator. And we also need to remember to de-init it here. So self context, self, come on, de-init, right? Something like that. Let's do a build debug. Debug is quicker to actually build. What happened? What did we do? We did something stupid, no doubt. Tuple declarations can what happened? What happened? I don't know what happened. Oh, of course, it's not supposed to be an assignment. It's a colon for a type declaration, remember declaration, or whatever we want to call that thing. Okay, so now we have a list of these guys, and here we'll want to actually clear it. So clear retaining capacity is probably the most obvious thing, because we'll have the not necessarily an equal amount of points if we retract or extend the cable, but for most of the time the cable's length is going to remain the same. So most of the time it's just going to be a very efficient thing to if we retain the capacity, and then we just start pushing things back to the thing. I can I can already see that we'll want to actually have the opportunity to throw some errors here. So let's just propagate this error handling thingy all the way back to the component. So ticking, pre-tick, and then we have tick, and this would then be try here, like so. And yeah, this can already handle errors on the component side. So we tick this guy, we pack the points, and right. So now then, 4, and well, essentially it's the same 4 as here, but we need to loop over it twice, because we need to, before we can actually start to process these things, we need to have these bounds calculated for us. And again, we want the position for the point, and we'll want to have scaled x, and this would be basis math remap float. So we have pos.x, we have old min, and this is now the bounds min. So we can do something like const. Actually, we can even do it outside of this for. So we can do const. What do we call it? Bounds min. This would be self cable packed visualization. Okay, we'll on bounds. This would be min. Just to make this like a little shorter to write. So bounds min. X. Bounds max x. And that would be 0. And it would be 2047. And then I can copy my comment here. Something like that. And for this we have 10, so that would be 1023, 1023, and that would be y. Actually, it's small x, y, and x, z, x, y, and z, and of course it's the same thing for that as well. Okay, xyz, 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 yeah, that looks good. And now we need to pack these guys into something. And how do we do that? How do we do that? I don't actually know how we do that. Why is it complaining about this? Is the redeclaration of right? That's why. I was expecting it to complain about all of them because we're not using them, and now it does it. Can I do this? Yeah, no. No. But I can do that though. So this should now build first of all, and it does. And right, we want to pack these guys now into an unsigned integer of 32 bits. And how the hell do we do that? So in the Zig standard library, we have this thing called mem.zig. And in here, we had something that if I can remember the name. Let me just quickly look up the name of the thing I was thinking about. Yeah, so it's write packed int. Write packed int stores an integer to packed memory. Okay. So I think if we, yeah, I think that should work. So if we do something like this, let's create a variable here to actually store that in. So we have a variable that we call I don't know, memory or something, and it is of type U32. You can just initialize it to 0, and that's the thing that we actually want to write to. Then we can do. We want to cast. So this guy is supposed to have 11 bits, right? So we can do packed X or something like that. And that would be, and we can actually in Zig we can do U11, right? And then int from float, I think. And we can do scale X. This is this is super scary because there's so many things here that are sort of I'm not super familiar with, but this should work. So if we do U11, U10, and U11, we get the packed values into those variables, and then we should be able to do std mem write packed int, and the type for X would be U11. Bytes is then std mem as bytes, and we give the address of the memory that we want to actually write to. Bit offset would be 0 for this one. We have packed X and endian I don't actually even know where's that. Is it in? No, where's this guy? Endian. What is endian? Yeah, where is it? Endian.little, I guess. I don't know. Endian.little with the capital L, something like that, right? No. Where's the thing? Built-in, std built-in. Okay. And here we go. Little, right? Something like that. I think this should work. So now we do the same with y, and we want to pack it into 10, right? And that would be at bit offset 11, because we wrote 11, and now we offset it by that, and then again we do the last one. So U11, and this would be Z, and the offset is then 10 plus 11, so 21. Right? Does this make sense? I think it makes sense. And now we can do try self cable packed visualization points, and no, this is append is what we want, and then we append the memory. Right? This is scary, but it might just work. It might just work. Yeah. I guess we'll have to write the unpacking function and then see if it works. I think that is kind of what we have to do. But before we do that though, let's go to our tick function, And we can do for self cable packed visualization points items, and we have just a point, and we do stream dot put what is it, put int u32 and p, right? Right int slice. Yeah, I think that should be fine. We should probably have some way of actually just writing a whole bunch of data to a stream. Maybe we already have that. We do like write, nope. Put string. This would arguably probably work, but let's do it like that. So now we're putting the bounds, and then we're putting the items. And before we put the items, what we'll actually want to do is we'll want to do put we want to put the amount of those points that we added there, so that we can unpack it on the other side. And so the type is, it could be a uint32 as well. And self cable packed visualization points capacity, no. Items, no. What was it? It's probably, yeah, it's a slice, so len is what we want. This might not actually work now. No, it expected u32 and we found an u size. So what we want to do here is we'll need to cast this, and we'll need to do like an int cast, right? I think if we just do an int cast, then it should work. Yes, because we're telling Zig that, okay, we're putting a uint32 or a u32 rather, but this guy is a u size. It's a slice, and this slice has yeah, well, it's a slice, and and the len of a slice is a u size. So int cast just casts it to the correct thing here, and the correct thing is determined by whatever it's trying to actually be put into. So this should work. I'm sorry, I'm hitting my microphone stand. All right, so that should be all the sending. And now what we can do is we can, just below this, we can or deserialize this stuff into members here, and then we can do the unpacking of it. So first we're putting in the bounds, and then we're putting in the length, and then we put the actual points. So we need to do it in the same order here to actually get the correct data out. So first we can do self cable packed visualization points clear, not clear and free, but clear retaining capacity. And we did that already here in the previous one, but this was of course in the pack cable points, and this is only done on the server side. So now we're on the client side here, and we need to do it here as well before we actually start reading into it. Right, so const point count equals stream dot get int, and it's a u32. Right, and now then we can do a loop with a counter like this, and again we can do point stream get int u32, and then we can do try self cable point bounds, no visualization points, append. And actually what we can do is we can do like reserve or resize. It's called ensure capacity. Yeah, so what we can do is we can do append assume capacity. We can just add the point there. But before we do that, we then need to do self cable packed visualization points, ensure total capacity point count. Something like that. And we need to try this. We need to try that, but we don't need to try this if we use the assume capacity version of that. And yeah, we need to. Oh damn! Yeah, that's. Pipe data received. Yeah, maybe we can make that. Throw errors, and then we can do try. Yeah, that should be fine. That should be fine. Yes. Okay, so what we're doing here is like in one go we're ensuring the total capacity of this guy. Maybe we'll actually do those things right after each other, and then without worrying about the capacity because we ensured it here, we can just append it. That should be perhaps more efficient than just appending and because the normal append just does this, like append allocates more memory as necessary, and yeah, this does not actually do any of that. It just pushes the new item there. Okay, good. So that should be good. Now the only thing that we still need to do is to unpack those visualization points. And we need to unpack them into something, right? We need to unpack them into something. And what is that something? Well, I haven't decided that yet because we don't know exactly what we're going to render, right? But I have to come up with something. So what I want to do here in update is I want to call basically basis debug draw line 3D, and I want to give it one vector 3 and I want to give it another vector 3 and a color. And I'm going to call that for all of the points to get the cable rendered for now. So given that requirement, it makes sense that we need a list of these vector trees to actually unpack into, right? So maybe we'll just do that and figure out what we need for cable rendering, right? Something like this, but for now we can do cable unpacked positions, right? std array list of vector trees, and we just do std array list of vector trees dot init context allocator, like so, like so, and we de-init it there. So now we have a place here where we can unpack two, and then we can render those guys, and we can do the rendering here first, just for funsies. We don't want to iterate over the whole thing, actually, we want to iterate over the whole thing -1, because if you have like 10 points, then you can draw 9 lines, right? So let's do it with a counter again. So we can do self.cable unpacked positions .items.length -1, and we only want to do this if self dot unpacked positions items len is 2 or larger than 2, because otherwise we can't take this -1 there. Okay. So now then, what we want is we want something like const p0 is self cable unpacked positions items I, and we want const p1 is self cable unpacked positions items I +1, and we want a color which is basis color, I don't know, orange. Well, what do we use? Let's use orange, and then we do basis.debug draw line 3D. We do p0. Oh, p0. Come on, p0. Okay, I lost the thing. I lost the thing. Right? That should work. That looks good. That looks good. I can just get rid of those. So now if we can still put in the last missing piece of the puzzle, which is unpacking the data, and get that working correctly, we should be able to render that stuff. So let's do that. Let's try to get the unpacking working. So fn unpack cable points. And I think it should look probably the same as for the pack cable points method. And unpacking essentially just the reverse of the thing. So we do self.cable unpacked positions clear retaining capacity. Again, it'll most likely be the same number of elements, unless you have extended or retracted. And not even always when you extend or retract, because like we only add one more segment, i.e. one more point, when we actually have extended or retracted so much that we actually have space for one of those guys. All right, so for self, and what did we call it? We call it cable packed visualization points dot items dot len, and let's call it p this time because it's a packed point. And yeah, so now that is essentially our memory, if you will, right? So now I hope that std mem has something called read packed int. Does it? I think it does. It does seem to have it. Right. So that would be u11, right? And bytes, std mem as bytes is p. Bit offset is 0, and this is std built in ndn little, and we can call this packed x, and then we can call this packed y and packed z. That would be 10, that would be 11, That would be 11, and that would be 21. Yeah. I hope I understand how that works. Otherwise, it'll be silly. So, then we have scaled x is, that would be like float from int, right? And packed x. Scaled y. Float from int packed y. And scaled z. Packed z. And now that we have these, we should be able to actually we should have like a const v, which is the vector, which is basis math vector 3 init, and we can do something like this, where we take one of these guys and we do scaled x from 0 to 2047, and at this point we have already done this part, so we have already read the bounds. So bounds min is that, and then we have bounds max dot that. Like so. That should be that. Then we have two more, and that of course is y and z, and that would be 1023, and that would be y and z and y and z. Like so. Yeah. What do we have here? What's the problem? Common float from int must have a known result type. Okay. Right. Okay. Yeah. It needs to know what kind of float I'm expecting out of that. Well, I expect a 32-bit float. Thank you very much. And then we do try self. What did we call it? Cable unpacked positions is what we call it. Append and v is what we append, and that's it. That's it. I think no, it's actually it's not it, because we need to add the parent position there as well, right? Add it back in like we did previously. Okay, so that built, at least in debug mode. Let's try to build it in release mode, and I'm kind of scared, but let's try to get that working in the release build. Like this kind of thing it can probably be expressed a bit more elegantly. Like we're just have these almost exactly similar lines here quite a lot. And I'm sure we can do that more elegantly if we want to, but oh, yeah, that didn't work. That didn't work. Actually, we're not even calling this guy. So that would be a problem. We can add it here, perhaps, but yeah, we're crashing. So let's go back to debug for a bit and see what we're doing wrong, and maybe if we put a breakpoint in here and we see what's happening, maybe we can figure out what is going on. All right, so we should have like 2 segments, I think. Yes. Okay. Go in here. I'm assuming everything probably Oh, no, no, no. What happened here? Int from float. Can we not create like can we not create like an 11-bit integer from that? Maybe we're not supposed to do that. Maybe we're not supposed to do that. Are we supposed to? Are we supposed to? Yeah, I don't know. Let's run that again. Let's go here, there maybe, and we'll just run that again. Yeah, this bitpacking stuff is completely new to me. I've never tried this. So, yeah, we have some. Oh, that's not good. If that is indeed what we have. It's a nan, so that would probably be why it fails, right? But what is pos? So pos is 3. Bounce min is also 3. And bounce max is also 3. Okay. Yeah, that's probably not very good. It is essentially infinitely small. Is that what you're telling me? It's interesting that I didn't run into this problem. I mean, this kind of makes sense, right? It kind of makes sense because if the cable is just going like straight down, then that is what would happen, right? But I didn't run into this on the C++ side, so I wonder, did my cable just never go exactly straight down? So what do we have in the cable bounds? Or actually probably in the cable segments. Yeah, but that's kind of tricky too. We can't read the world transform out of that. But we can read out of the cable point bounds. And we can see here that yeah, the z coordinate is exactly the same and the x coordinate is exactly the same. The y coordinate is not. There is half a world unit between those two, as you would expect, because the segments are half a world unit high. So we have two segments going straight down. That is completely fine. That's absolutely fine. It's just the problem that that now we can't remap these floats if the old min, new old max, and oh yeah, if the old min is the same as old max, we can do that. So what do we do about that? I'm thinking that we'll need to probably detect that this thing is like infinitely thin somehow. Do we have like a size checking thingy here on the C++ side? I mean, I can easily do that, but yes, I have a get size here. So maybe let's add a get size here to the zig side as well. So, well, we're gonna get extents essentially already, but let's just add quickly like a get size. That will be self. This could be a const. And do like void, and we can return max minus min, right? So self max sub self min. that is effectively gives us the, oh, that's not supposed to be a void, that's supposed to be a vec3. That effectively gives us the size of the bounds, and if any of those things are too small or like very close enough to 0, then we need to expand those bounds a little bit. So check for infinitely thin bounds along all 3 axes. So std, sorry, it's basis math. Floats almost equal. Actually, first we do one thing first. We do const bounds size self cable point bounds get size, and then we do this. So we do 0, and we do bound size x. So if we are if we are 0 along a certain axis, then what we'll want to do is this. Let's add like a const bounds epsilon and bounds. What do we call this? 0 bounds margin or something, and this would be very, very small, something like that. It will cause a visual discrepancy, but the cable is almost never going to have bounds that are 0 along one of the axes. It's only really when like during the first frame of the game, when no physics have been really simulated or anything like that, that is when this can happen. So it doesn't matter, and this thing will then not be the case anymore the next frame. So it's fine, and we're moving it like what is that, like a 1/100th of a centimeter or something, so completely fine. Okay, so if we are if we're almost at 0 along x, then what we want to do is actually I'll just, yeah, I'm just gonna do. I was thinking I would be fancy, but I'm not gonna be fancy. I'm just gonna do this. Check along all of the axes, and if can I actually break this, or will the formatting be unhappy with me? Yeah, it does work. So if it's 0 along any of those, we'll do a margin, and we'll take the bounds max, and we'll add a vector3 with those margins, and we'll just expand it along all 3 sides, because like I said, no one's gonna notice if the bounds are a little larger for like a single frame. It's not going to be visible, like a sub-pixel thing. So we have the margin, and then we'll simply add that back in. So we take the max, we take the max, we make max a little larger, and then we'll add it in, and that should be fine. Actually, maybe we can run it in debug first to make sure that this actually fixes the problem, and that we get like sensible values out of there. So let's build debug. Should build very quickly, and then we run the game. And of course the game is not as quick when we run it in debug, but that's fine. So now these should have some sensible values. Yeah, they have 0, 122, 0. That's completely fine. Yep, that looks good. And we pack them into some memory, and the memory gets some value, which is kind of tricky to interpret like this, unless you're really good at reading binary. But that's fine. So now we can get through this. I bet the unpacking works as well. So the thing that is now missing is unpacking, calling unpack. And we have this thing here where we're checking, like, do we have any unpacked positions in the list, or actually do we have 2 or more? And if we do, then we try to draw it, but we're not actually unpacking anything. So we need to do that first. And here is a very important thing to do now. When we are packing them, here, we're using the transform get position. So that is the uninterpolated position on the server. On the client, we use interpolated positions. That is why you see, occasionally you see those physics visualizations sort of jumping back and forth, because they're using interpolated positions, while the client is typically using interpolated. And here we want to definitely use the interpolated position of the vehicle. So what we'll want to do is something like this. We'll want to do pos. You can even call it interpolated pos. So do self context get render. No, is it transform maybe? Get render scene node. Get position. Actually, we want the get position in space, and that would be space world. So world space position is what we want, because this render scene node is interpolated. So getting its position gets you the interpolated position. And now we can do self unpack cable points using the interpolated position, and that doesn't work. Space world. Is it not called space world? What is it called? Okay. Oh, come on, basis math. Coordinate space. Oh, it's just called world. Okay then. So I'm trying to use those shorthand versions as much as I can. Right, and I need to try this, which means that I need to make that tryable, and that also means that I need to try this. So where is the update? It is over here, and we need to try that. usize does not support indexing. Oh, of course. We don't want the len there, we want to iterate over the items. Expected single item pointer past U32. What? Where? So type is that. Bytes is that. So I'm guessing this is probably like these lines are probably the problem here, right? If we just take those out. We're not using P though, so we're doing something wrong here. You can immediately see. Let's figure this out. Because right, it's okay. It's as bytes P there. Yeah, so that doesn't work. Why does that not work? Read packed int. Let's go have a look. Oh, is that the problem? We need to give it. We need to pass it the address of P. In hindsight, that makes perfect sense. I'm gonna assume that is the thing. Yeah, that was a problem. Okay. Yeah, we could have maybe just done this once and then let's maybe do that. So we have what is this? That's just a as bytes return type. I don't know, but let's do like const const though. Yeah, I think this is const, isn't it? So U8 bytes U8. Can we do like memory pointer bytes or something like that, and then do std mem as bytes address of memory, and then we pass this. Right, that should be able to be const, right? Because this memory variable needs to be writable, but the pointer doesn't need to be writable. So we can just do that. Then we can maybe even just use the same name here. Boom. Yeah, okay. Okay. Yeah, let's hope this works. Should work, I think. Yeah, it succeeded, and what do we have? Well, the game runs. Doesn't look like it's crashing, so that's good. Do we have a thing? Do we have a thing? Hey, we have a thing. We have a thing indeed. So now we can turn off the server side drawing of physics shapes, and we can revel in the fact that the cable is being rendered by and on the client now. So that's fun. Now you can see that this cable is actually, you can clearly see the sort of the vertices here, because we're not doing the thing we did on the C++ side, where we're actually generating like a Bezier curve out of this. I'm not sure we're going to actually do that. Like now, this is rendered using debug draw, which is not what we're going to actually be rendering the cable with. We're going to actually generate a mesh out of it, and I'm doing weird things with my crane arm there, so things break. Yeah, it doesn't really I don't have any limits on how you can move that arm yet, so I mean I kind of have, but I don't have any checks in the code to make sure I don't do anything stupid. But yes, yeah, we're going to be generating an actual mesh on the client for this, using these points that we have sent over. And when we have an actual mesh created out of them, we can, for example, have the cable cast shadows and do other things like that we can't do with just this debug drawn geometry. And yeah, you can clearly see the positions that we've sent over. But that's fine. That's fine for now. this was what we wanted to get done this time around, and we did it. And I think the next thing is I'll probably expand on this thing a little bit, and I'll put in the end magnet as an actual mesh, because now, of course, we have this magnet thing on at the end, which is actually really tricky to position because this physics visualization that you can see here doesn't have any shadows. Once we get shadows added for it, so when it has an actual mesh that casts shadows, it should be super easy, or much easier, to actually position it correctly in 3D space. So I'll do that next, and then I think in the next episode on video, which should be sometime next week, adding the mesh should be pretty simple after all. I think we'll do something other than programming for a change. I think we'll do a little bit of 3D modeling, try to figure out how we want this crane arm to look. And there are all kinds of interesting things that we can try to do. So that should be great fun. But yeah, this was interesting because now we have essentially now we have everything ported to Zig that I've ever had done for this crane. There's nothing that I've had done in C++ that I don't have, if we don't consider the Bezier curve generation, but that's not really a crane thing. So everything is now ported. That's great, because I like writing Zig much better, especially for this kind of gameplay code thingy, than I like C++. Anyway, I think that's it for today. I hope you enjoyed this brief look into bitpacking and other fun things in Zig. And I'll hope to see you in the next one, where we'll most likely be doing something completely different, 3D modeling. That'll be fun. See you then. Have a good one, and bye.